God damn them all. I was told we'd cruise the seas for American gold. We'd fire no guns, shed no tears. All right, we're live. Internal energy. So, internal energy. Okay. I'm probably going to screw this up a lot. Back in college and grad school, I only ever saw internal energy referred to using the capital letter U. Okay. The book uses E, just for E for energy, right? So don't be surprised if when I'm talking about this, writing about this, I use the capital U instead. All right. So what is internal energy? The internal energy of a system is every single tiny bit of energy in the system, which means we can't measure it. There's just too much stuff, too many different ways energy can be stored in a system. So unless you're talking about a really small handful of particles in a pocket universe, you cannot actually measure the internal energy of a system. So instead, we talk about the change in energy. So delta E, the change in the internal energy. We cannot know the total internal energy of a system. We can know the change, because a system can exchange energy in only two ways, heat and work. That's why we've been talking about them this whole time. So delta E is equal to Q plus W, the amount of heat going in or out, the amount of work being done on or by the system. So the change in the internal energy of our system is Q minus P delta V. So there are a couple of different things that make this simpler. Okay, constant volume. Okay, so we signal that something is being done at constant volume if it is. We put the little capital V as a subscript. So at constant volume, delta V is equal to 0. The system can't change size. Therefore, delta V is equal to 0, so work is equal to 0. So that means that the change in internal energy is going to be equal to heat. Okay, at constant volume, a constant volume system, the system can only exchange energy through heat. Okay, so all you have to do is measure the heat. And that's really easy to do, actually, because you just measure the temperature of the system. And here's the thing. Energy is a state function. Okay? Heat and work are not. Okay? But if heat is the only way the system can exchange energy, then that means for a constant volume setup, heat becomes a state function. So all you have to do is measure the initial and final temperatures of your system. You've measured the heat exchange by your system. You've measured the change in the internal energy of your system. This is wonderful. Temperature is really easy to measure. So you just set up a constant volume system. Boom. Measuring temperature tells you a lot about what's going on inside your system. But we can also work at constant pressure. Okay? At constant pressure, well, it's slightly different. Still Q minus P delta V. Okay? So you rearrange it, and Q is equal to delta E plus P delta V. But here's the thing. Delta E is a state function. P is a state function. Delta V is a state function. These are all state functions. So Q, heat at constant pressure, is also a state function. Now, it's not the same thing as internal energy. Instead, we call it enthalpy, delta H, where delta H is equal to delta E plus P delta V. So it's related to internal energy, but it's slightly different. So that means that we have two different ways of measuring a lot about the inside of a system without having to do a heck of a lot of work. At constant volume, the heat exchanged by a system is equal to the... I told you I would screw this up. Delta U instead of delta E. Whatever, doesn't matter. But at constant volume, the heat exchanged by the system is equal to the change in the internal energy. And at constant pressure, it's equal to enthalpy, which isn't the same thing as internal energy, but it still gives us a lot of information. So long as we're working under one of those two conditions, constant volume or constant pressure, then we can figure out a lot about the energy change associated with a reaction by measuring heat, which means just measuring changes in temperature. This is really, really valuable. Okay, because the change in the energy of the system is going to give us a lot of information about why chemical reactions happen. Okay, so good news. Heat is easy to measure. Energy change is really important for understanding why chemistry does what it does. And we can ignore work. Work is stupid and bad and a lot more difficult to measure. Kittens are cute. That's irrelevant, but I feel it's worth mentioning sometimes. Delta U and delta H, okay, change in internal energy and change in enthalpy are really close most of the time, so it's kind of a wash. We mostly only care about delta H, change in enthalpy. In chemistry, there are times delta U becomes important, or change in internal energy. There's also a couple of other different things, but we don't care about those for now. Right now, we're just going to focus on delta H, and heat is really easy to measure. So, just to give you an idea of what we're talking about here, constant volume, that just means building a very stable device, a box, a bottle, a very stable, very strong thing that won't change volume. And that is called a bomb calorimeter. Bomb because it can't change volume, so if you increase the pressure too much, it might explode. And constant pressure, that just means you're working with an open container on a bench top. Okay, so we talk about enthalpy a lot in chemistry precisely because most of the time that's what we're working with. We're working just with an open container, and if the container is open, then it's constantly being exposed to atmospheric pressure, and the pressure is not going to change. So it's just a constant pressure setup. This one kind of gives you a more direct line into what's happening inside the system, but it requires a little bit more effort and expense to set up. Not a heck of a lot, but a little bit. Whereas constant pressure, it's a little bit more work on the back end with working with enthalpy instead of internal energy. But it's a really easy thing to set up. All you have to do is leave your container open, sitting on a bench. I mean, it's really great. So heat is really easy to measure, and because under these conditions it's a state function, that means that all we have to do is measure the initial and final temperature, and we have discovered just a heck of a lot of information about what's going on inside the system. Okay. So those are the two things we get out of this. At constant volume, heat exchange is equal to the change in internal energy, and at constant pressure, heat is equal to the change in enthalpy, and either way, it's a state function. That is really awesome. So that is it for internal energy. So now we'll talk about how we measure heat. See you in a few minutes.